to tell you guys about this pretty surprising and strange little system. It's a kind of an oddball, but I hope that by the end I'll convince you that there are actually a lot of broad applications and potential consequences and implications of it. There will be an observational piece at the start, and then there will be a theory plus dynamics piece towards the end. Okay, so this is a story about compact stellar binaries, and I think that if I draw a stellar binary like that, that has an orbital period of, we should think about a couple of days, I think that immediately the naive expectation should be that, well, the compact ones will tend to synchronize, the stars will synchronize the spins of their companions. And so the sufficiently compact binaries should have their spin periods equal to their orbital periods. And so if I make observations, they should lie along this red dashed line. Now, if the binaries are slightly further, that's such that they're not close enough that tidal interactions become important, their spins should be roughly evolving as if they don't see their stellar companion. And so they retain some primordial rate. That might be dictated by spin down, formation, etc. Point being, there should be no strong correlation here. That's kind of the most naive thing, but if you go out and you want to test this hypothesis, the best way to do this is to use asteroseismology. That gives you the best constraints on the spin rates. And this was exactly what was done a couple of years back. And this is kind of the trend that I saw. Based on what I just showed you earlier, I think you should find this very encouraging. I have exactly a cluster of points lying along this red dashed line, and then I have another cluster of points over here, rapidly spinning stars, but that are sufficiently wide that they are not synchronized. Problem solved, right? Not quite. I've actually hit it. I've hit it from you 4 points earlier. Out of about a sample of 35 points that this particular study looked at, they found 4 of them that are exactly on the wrong side of this red dashed line here. These are very close in binaries that seem to show evidence for spinning very slowly instead. Here I'm going to focus actually on the least subsynchronous. This is an eclipsing binary, and the other ones I will not be talking about here, but you can ask me about later if you're interested. Okay, so how do they actually get this result, right? The primary here is a 1.6 solar mass gamma Doradus pulsator, which means that it will self-excite the pulsations. These are the pulsations that you see. There are 4 peaks. And based on the spacing between these peaks, it turns out that the spacing tells you something about the rotation frequency compared to the frequency of the modes. This is the period spacings are down here. And you can see from the y-axis here that the period spacings are almost exactly uniform, which has to mean that this F drop here is extremely small. That's the origin of the slow spin constraint that they find. This is nice and simple and all. Is there any way that we can corroborate this? Well, okay, sorry. Let me start building a schematic here. This is going to get a little bit more complicated, so let me go ahead and introduce it to you now. This is my 2.7 day system that has a measured spin period of 38 days of the primary point here. Okay, so how might we also be able to handle the story? Maybe we can go after the spin in a different way. A way that might be familiar to exoplanet folks is the Rossum-Colossal effect. So since I have an eclipsing binary, one of my stars is spinning, so half of it is blue shifted and the other half is red shifted from us. And when a secondary passes in front, it will first block out the blue, and then the red shift which would be the signature that you get if the orbit and the spins are aligned. And the amplitude that's broadening is also going to give you a constraint on how fast the star is rotating, right? If the star is not rotating, there's no signature. This also happens to pop out some information on whether the orbits and the orbit and the spin are aligned. If they're misaligned, this might tell you that, oh, something interesting dynamically happened. Maybe the star is still evolving, it's still synchronizing. You will get a different signature here if the orbit crosses in a different way, not the aligned orientation. So we went after this over with a couple of folks at Princeton, and with this beautiful little visualization, you can see that the secondary crosses in front of the primary, and it's aligned, very good accuracy, and the surface spin is exactly the value that you expect. It is synchronous, it is equal to the orbital period. Okay, so this is where it starts to get a little interesting, right? Because if I take my schematic earlier and I zoom in on the primary star, our new observations show that the spin is actually, the surface of the star is spin aligned, exits spin orbit alignment, and the spin period is 2.7 days, exactly as we expect. However, somewhere in the deep interior, due to this asteroseismic constraint, you have a spin period of 40 days instead. That's spinning very, very slowly. So this seems to suggest that the star has some strong differential rotation going on inside, right? The last little piece of the observational puzzle that we're going to need to use to build our theory picture is that there is actually an observed tertiary companion. It's a low mass and dwarf. Its mass is probably somewhere around 0.4 AU. 0.4 solar masses, and it orbits on a 3,000 day orbit. The question now is that, well, there's nothing weird about the stellar binary from a stellar modeling perspective. So this stage is probably out of order somewhere like gigayears, right? It's not megayears or anything weird. So the question is, how do you sustain this really weird spin state over an order of gigayear timescales, given that your primary should have synchronized within about 10 megayears or so? So that is the theory puzzle that we're going to try to deal with here. And I'm going to propose that you can explain this if you make the picture a little bit more complicated, in fact, by claiming that the interior of the star actually spins in a misaligned way. It spins on its side due to something called the spin orbit resonance, which I think that some of us have heard about to varying degrees. So the old idea that's been around, that's floating around in the solar system for many decades. So what is a spin orbit resonance? Let me take a quick dynamical theoretical intermission and explain this to you guys real quick. So in order for the spin orbit resonance to occur, there's going to be a commensurability between two precession frequencies. The first is going to be the spin precession of the star, which is oblate due to its own spin, driven, let's say that it's just some star for now. It doesn't have to be this particular weirdly spinning one. It's spinning, so it's oblate, and it's going to get torqued by its binary companion. This torque, it will tug on the equator like this, and when the star comes on the other side, the equator will be tugged on the other side. This results in a torque on the star that will cause it to precess, as I will show you momentarily. I want to highlight briefly before I move on from the schematic that you can imagine that if I take this sine ellipse and I tilt it a little bit more, the torque on the primary will actually be a little bit smaller. What that suggests is that the precession frequency does actually depend on this theta angle, which is the spin orientation of the star with respect to the binary. That's something that's going to come handy a little bit. So all you need to know is the torques do depend on the geometry, the spin orientation of the star. Okay, so the precession that is driven is going to look something like this. You can imagine now that my star wobbles around a little bit due to the gravitational forces from the companion. And in particular, what that will do is that the red spin vector here will trace out a little conical shape about the orbit normal, which is pointing vertical here from. Same exact exercise shows that if I have a distant binary, a distant tertiary companion, then the orbit of the inner binary will also be driven to precess like this. So the blue vector itself will precess about some distant orbit normal, the black vector there. Okay, it's a lot of moving arrows. If I let both of them evolve, what will generally happen here, I'm going to remove the tertiary because it doesn't really do much. I'm just going to keep track of its orbit normal here. In general, because the inner binary is so compact, you can see that the red vector precesses really, really rapidly, while the tertiary is really far away. So this blue vector will move around very slowly. So in general, the dynamical picture that you would expect looks something like this, where the red vector is doing this crazy little thing, the blue vector is moving very slowly, because the spin orbit precession frequency is much faster than the precession frequency of the orbit of the binary. However, I pointed out earlier that there's a geometric factor. If I let the spin orientation, the spin of the star tilt more and more onto its side, an interesting thing will happen. You can see here that, one more, there we go. Okay, right here you can see now that the red spin vector will always point away from these interior two vectors here now. This is because as my theta vector gets close to 90 degrees, this actual precession frequency becomes commensurate with the orbital precession frequency, and at that commensurability, something dynamically interesting happens. The red vector always points away from the other two guys now. This in hope that video plays. Yes, okay, so if you really do your dynamical analysis, you will find that this is truly a dynamical resonance where the spin vector of the spin state of the star consists of circulating trajectories, either the green, which will go all the way around, or light where the red vector you can see always consistently points away from blue and black vectors there. If you're not as interested in this, that's fine. I just want to throw this out there for dynamical folks. But okay, there's something really useful about this. Let's try that again. There we go. There's something really useful about this misaligned state here. These red guys, the ones that I showed you that were vibrating, they are protected against the influence of alignment tools. So if I start with a range of initial conditions like this, and I say, let there be tides, let there be something, let there be dissipative forces that drive my spin towards alignment with the orbit. Okay, so this is a very sped up animation of what's going on here, but I think you can already start to see, right? All of the red vectors stay equatorial, while all of the green and the blue vectors are driven towards alignment with the orbit. So you can be protected against tidal alignment as long as you're stuck in this weird red Cassini state 2 resonance.
Some of the blue ones enter.
Yes, that is exactly true. That is a weird little mathematical process that does occur. It's a low probability event. You might have seen that there were a ton of blue vectors here and only a couple enter. You can calculate this capture probability. It doesn't. It should. That's right. Good sharp eyes. Okay. So there's one last little piece of dynamics that I need to cover before we can get back to this weird little system. Why do I care about misalignment, right? I've been telling you the story about orbital periods and spin periods, but suddenly I went on this whole tangent about, I can misalign this. The reason is that as long as something is holding your theta, your liquidity, near 90 degrees, then you add some tidal dissipation on top of it, it turns out that the actual spin rate that you get becomes very slow. You see in the cyan region here. The equilibrium spin rate is actually much slower as long as there's liquidity near 90. So if I can use my spin orbit resonance to keep myself trapped in a near 90-degree liquidity state, then tides will act to drive my spin also to a very synchronous rate. So let's put that all back together. Let's bring this little graphic back. The proposal then is that the core of the star spins on its side, spins very slowly because it's caught in a spin orbit resonance. You'll notice that the cyan has shrunk a little bit. I've put in more typical values of what you should expect for such a network like this based on MESA models. Okay. In order to be caught in this state, again, as I mentioned, as we saw before, if we add a little bit of dissipation to the system, then you will be driven towards this long-lived, misaligned, slowly spinning rate. Earlier I said that this dissipation could be due to tides, but the core of the star is so small. The tidal dissipation inside there is probably not very strong. In fact, what you might expect instead to be the case is that stars don't like spinning with a lot of differential rotation, right? There's some torque that should counterbalance this very weird state, where it tries to restore you to uniform rotation on some characteristic coupling time scale. So you can imagine that this coupling time scale is going to take the core of the envelope and try to bring them back towards alignment and towards synchronization. This is kind of the toy model that I put up there. The processes for actually doing this are not super well understood, but we can turn it on its head and say that, well, if we understand what happens in the system, then we've constrained coupling processes a little bit. So you put in a coupling torque that looks something like that. That produces the dissipation that you need in order to turn your misalignment into a subsynchronous spin, and the whole present day picture and the observations kind of all line up this way. The last comment to make is that if we demand stability of this very slowly spinning state here, that requires that the torque that I don't know why that disappeared. Let me try to press it right again. Excellent. Okay. It demands that this torque that I put in up here, the coupling timescale has to be greater than about 50 millimeters or so. Otherwise, this resonance is so fragile, you put a little bit too much dissipation in, and suddenly it will break, and you will be driven back towards alignment. All of that, other than this brief parameter here that's not well known, the rest of this is all very compatible with kind of what you would get if you just take stellar evolution codes, you run them forward in time. you get exactly what you want. Okay, last but not least, this is just the present day configuration of the system. It turns out that you can tell a dynamical story about this as well. Because if you go back to when I showed you this video about capture into the resonance, you might have noticed, again, other than these little blue dots, it's only the red dots, the initially misaligned systems, that are able to stay misaligned. Also, yes, a couple of the blue ones that are all retrograde also do misaligned. But the point being that nothing aligned is able to get kicked into misalignment due to this dissipated process. So if the system today is red, it's in this resonant region, then the initial state of the system could not have been aligned either. So at some point in the distant past, the system must have experienced a lot of misalignment, which is kind of, I think, a smoking gun for some sort of a dynamically interesting, dynamically active formation channel. And this is something that has been proposed for a long time now for the formation of these compact binaries, something called the Bazzagli-Cosi effect plus tidal dissipation. Okay, so I'm just gonna show you the setup. I'm gonna show you the evolution. I don't think I have time to go into too many of the details about the process. But these are kind of the initial conditions that I'm now considering. You imagine an inner separation that is modestly larger. It's about a factor of 3 to 4, larger than present day separations. And you have a tertiary that is on a quite misaligned 70-ish degree misalignment orbit from the inner binary. And then you kind of just throw the kitchen sink at it. You throw your orbital evolution in, you throw your core envelope coupling in, you throw tidal dissipation in, you throw all of these things in. And there's a zoo of effects to consider. But this is an example of the sort of evolution that you get up. The key features to point out are that, one, well, indeed, you started at a wider orbit and you eventually coalesced to the present day value shown by the black dashed line here. The reason this occurs is because your inner orbit will grow to large eccentricities and then come back to circular, and it will kind of oscillate like this due to this ZLK phenomenon. And over the course of these high eccentricity phases, you get a lot of extra tidal dissipation, which allows your binary to migrate, to compact, to harden. The last feature to point out is that, well, actually, my core, it looks like, is actually able to spin much, much slower than the measured value here of 40 days. That is actually okay. It's okay that the boss does this, because you should remember that if you go back to where we got this 40 days is a envelope average rotation rate. And here I am actually calculating the rotation rate that would be expected at the core. So you know the core is spinning super, super slowly. It couples the envelope a little bit. The base of the envelope might be pretty slowly spinning as well. So if you measure the envelope, you get something that's a little bit more modest than what true core rotation rate is. So I think that this is actually also consistent. And then lastly, the comment in the numerical integration that we do, about half of the time it ends up in high liquidity state, half of the time it ends up in the low liquidity state among the systems that actually stick with this. Okay. Oh yeah. Okay. This is the fun one. Since we are having a lunch talk, I thought I'd recast this in a sweet little story, a dynamic retelling of a dramatic retelling of the dynamic story. This is a story about two stars born far apart that are brought together by the vicissitudes of life. As their hearts fall for each other, time itself seems to stop. Their gaze is black, and they live happily ever after. Okay, so that's the summary of kind of the story that I think matches the observation test. There's actually real interesting reasons to be interested in the system, other than a little romantic tale. I guess I have a couple of minutes, so I'm just gonna put all these up, and that's not legible. Let me go back and. Oh, these animations are okay. Yeah, okay, then I'll get the active version of this discussion. The system does seem to present strong evidence for strong differential rotation, and among a couple of other systems that are observed in these compact binaries, it's not the only system that seems like it has evidence for deep slow rotation, but all of these other systems have only been constrained asteroseismically. We've been able to follow stuff with Roster-McLaughlin measurements to check that the surface is indeed doing something different from the core. This does pose some constraints on your core envelope coupling, which does have applications, I think, for black hole folks that would, I'll tell them about later. If the spin orbit resonance is actually the correct explanation, which I think is the only one that we have so far that matches these two observational constraints, I think that this is the first evidence that we have that one of these very high obliquity, this like very spinning on a side state, can actually be tidally stable. It's theoretically expected, but it hasn't directly been observed, I think, as far as I'm aware. And I think that it's an independent line of evidence showing that these compact binaries had both dynamically. I think that the open questions, the hope is that, in fact, there's been some, one of these interesting points is that the careful asteroseismology suggests that if you do this really, really carefully, you can actually probe the rotation profile as a function of radius. So my system only has 4 modes, that might be kind of hard to do it for, but maybe as I discover more systems, we'll be able to find more systems like this, 10% of the currents rate, right? And if we find enough modes in them, we might actually be able to do the differential profile. Okay. And I'll take any questions that you guys have.
Super cool. And I did wonder about you mentioned the 4 other ones with very large error bars, but there was also one with really short orbital period that stood out. You go really all the way back to
very. This online keynote is very laggy, unfortunately.
Oh yeah, that's one. The kick 833. That's because it's also off by a factor few.
Yeah, and there's not really error bars on that, right? Yeah.
No, it must be very, very good.
Yeah, I guess the orbital period, you're looking at something that's sub-day, so it might be in a compact binary regime, so maybe something weird is happening there at that point. I hadn't actually noticed that previously.
And I guess another question is, without the eclipses, you can still measure V sin I and at least see whether that's consistent with rapid spin, right?
Yes. Yeah, that's definitely true. For some of these systems, they try to do just the rotation, the constraint V sin I from the spectroscopy directly. The problem with that is that one of these previous analyses, they actually arrived at a very similar conclusion for the KIC 985 system, but they said, the surface is, seems like the lines are very broad, it could be spinning very rapidly, probably macro, because it's too inconsistent with the core rotation rates.
So your pictures would now say, hey, it's actually quite.
Yeah, I think it's actually correct, right? You can't break that generously without something like loss.
Yeah, no, that's fantastic. That's really great.
Hi, great story. Can you go to that, show the picture of the differential rotation, you know, the in the core is going, yeah, this one.
Yes.
Okay, I have trouble with this picture.
Oh, sorry. Yeah.
This is known, I think Poincaré is the first person, one of the early persons to investigate a star doing this. What if, you know, the interior and the exterior rotate different axes? I think his argument is that this is not possible because you get strong hydrodynamic rotations. Because the surface of constant potential and surface pressure due to the ellipsoid due to the rotational broadening, pressure variation, potential variation are not parallel. So this was what bugs me all the time. Never liked these configurations.
So I'm not familiar with that argument.
But just to imagine, right, the outer layer is rotationally flattened, and the inner layer is sort of spherical. Yes. So if you want to do a sort of continuous solution, you couldn't find one.
Well, okay. If we just pretend the core is not rotating initially first, right? You can solve for the structure of that deformed star as well, right? You just need to integrate your perturbed hydrostatic equations with
you have smooth profile.
Yes, so you can do that. The way that we've set it up in this work is that if you compose the perturbations due to the deformations into one driven by the slowly rotating core in a non-rotating envelope, and another driven by the rapidly rotating envelope in a non-rotating core. And both of those are.
But they're not thermally stable and not hydrodynamically stable.
They may not be hydrodynamic. Okay.
There are also another issue is that this is a gamma-rated star, so it's mostly F-type star. So there's nothing happening. Is it something strange at 0.1 radian?
That is the convective core radius envelope transition. That's the 0.1.
Oh, so this blue one is really tiny. So
Yeah, and later it becomes 10.
But the gravity mode don't probe, gamma radius, gravity mode don't probe the electric cord.
They broke the space of the, I actually have a slide for this. And so that's what I was arguing about, like, if the core is spinning with a 100 degree, then the base of the envelope, right here, maybe is spinning with 40 degree instead. So,
Okay, so.
so there has to be, it can't be exactly a 2-tone model, yeah, that's right.
There's something,
So there, it's important to be defined.
And unfortunately, we do have people signing up, so let's take both our speakers again.